Friends, today we are going to discuss a very important topic. This is called the system resistance curve. A pump operates at the intersection point where the system resistance curve meet the head versus Q curve, performance curve of the same pump. Here, if you see the picture at the bottom left hand side, you can see the pump. You can see at the bottom the pump and then a control valve, and you can see that control valve, and there is no elevation difference. Pump is taking suction from the same level, discharge is also from the same level. So the curve, system resistance curve, will be mostly the not static head, only mostly friction. And the second picture, if you see, in the second picture, if you see the that is the pump taking suction from the horizontal, and it is giving discharge to a tank having static head H0. So it is mostly the system resistance curve will be mostly static head related, and if it is a combination of both, then you can see here that it is taking, this is the right hand side picture, that is your static head, that is H0, plus it is your head loss due to flow. There is a volumetric flow, this is a head loss. So this will be your new system resistance, static head plus head loss due to this flow. Head loss, difference head loss. So if you add static head plus the head loss, you will get the flow of the pump, particularly for this point. Similarly, if you go on increasing the flow, the friction loss will increase. So you have to add it with the static head to get the system resistance. And when the system resistance will cut the performance curve, that will be your operating point. So you know the friction loss formula, that is Darcy-Weber curve equation, that is FL V square by twice GD to FL V square by twice G and D, where HA is the frictional head loss, A is the frictional factor, L is the length, D is the diameter, both are same, and V is the velocity, meter per second, and G is the acceleration due to gravity. So you have to calculate first. I have to know what is the value of F. Here we are giving the tabulated form some value of F. For brass tube it is 130, for cast iron it is 100, and concrete tube it will be 110. Like that, for any standard handbook you will get the value of this. Hydraulic books you will get the value of F. You know L, you know D, you know velocity, so you can calculate what will be the friction loss of this friction loss due to flow of the fluid from the pump. You have to add with the static head, then you will get the total frictional loss, total differential head discharge head. And suppose you are providing some valve or some T or some elbow, then you have to convert all these fittings into equivalent its length. Equivalent is equivalent straight length. Suppose you have provided a half-inch pipe, you have provided a ball valve, then it will be how much? Now 0.41 into inside dia. That will be your straight length. If it's a 90-degree elbow, 1.55 times into 0.66, that will be equivalent. Instead of this elbow, you have to consider that 1.55 into 0.6622, that will be your equivalent. That will be your equivalent pipe length, half-inch pipe length. Similarly, for different for angle valve it is 7.778. For globe valve it is 17.6 into 0.66. That will be equivalent length if you don't consider the if you want to consider the globe valve in the discharge line. So you will get, by adding all this, you will get the total length. Now you know the formula FL V square by twice GD, and then from there you can calculate the friction loss. What is the most stable operating point of the pumps in the curve? You know the best efficiency point, where efficiency will be maximum. And your operating point should be plus minus 10% of the best efficiency point. Here efficiency, power consumption, maintenance, everything, power consumption will be minimum, maintenance will be minimum, and where then your preference should be to keep your pump running plus minus of best efficiency point. If it is too far from the base efficiency point to the left hand side, then we call operating to the left of the curve. If the pump is operating right side of this base efficiency point, then we will call operating to the right side of the curve, right of the curve. What is too far, if it is left on the left side to base efficiency point, what will happen? Due to less flow, there will be heat generation will be there, and when heat dissipation will be less, so there is a chances that there is a rubbing chances is there. Your efficiency will lose. There may be contact between because due to high temperature, there may be a contact. It may evaporate also. So too much left side from the best efficiency point is not acceptable. Similarly, if it is too far from the best efficiency, right hand side of the right hand side of the best efficiency point, then what will happen? Greater tremendous sound will be there. Maintenance cost will vibration, noise, etc. will be there, and cost of the maintenance cost will increase. And there is a danger of flow is increased. When the flow is increased, then cavitation, the NPC requirement will also increase. You cannot fulfill this NPC requirement, then certainly pump will run cavitation, under cavitation. So what is the importance of system resistance curve? Suppose system resistance curve is there, it is running, pump is running. If you know the system resistance curve, you come to know which point it is running, If it is, I have already told you, if it is there is no elevation difference, then it is this is called steep curve, friction dominated. If there is a static head is there, then it is static dominated system resistance curve. So anyhow, but best efficiency, if one it is running, the running where your pump will be running, where the system resistance curve, the performance curve. That will be your running point. So you can come to know how far it is from the BEP point, best efficiency point. Suppose it is far away for right hand side from the base efficiency point, then friction loss will increase. So you can think of whether 2-3 pumps can you install instead of one pump, then certainly your friction loss will be increased. Suppose in one pump running the velocity is 5, but if you are running 2 pumps, then velocity will be 2 and 3 for each pump. So velocity square, friction loss will be velocity square. In first case, one pump, it will be 25, but in second case, it is 2 square means 4 and 3 square means 9, that means 14. So friction loss will be less. So you can think of like this. If you know your operating point where it is running, you can come to know what the solution will be. So it may be due to the clog, it is too left side from the BEP point. That means there is a restriction in the pipeline. There may be a choking. There may be an orifice may be provided. You might have forgotten to remove this orifice. So like this, if you know the system resistance curve, then you come to know where the pump is running, and accordingly a good decision you can take. This is the one example of a pump. It is earlier also you have the flow is you see it is a flow 500. Friction resistance is 58 meter. 58 meter. How this 58 meter has come? Now it is you see it is a 58 meter friction resistance, that is due to your inlet line is 3 meter distance from the tank. outlet discharge tank is 302 meter. So when the fluid will flow through this tank to the pump center line, you have to pass through the 3-meter line. There will be pressure drop of how much? Now 0.393. And for the discharge high pressure, when it is passed through this 302-meter pipeline, then the pressure drop will be 57.2 meter. If you add both, then it will be 58.2. 58.2 friction loss. Static height is 58 because it is discharge tank level is 61, suction tank level is 3. Though there will be difference, so there will be how much? Now 61 minus 3, that is will be 58 is will be your static height, and friction resistance is 58. So what will be your total head? Now I have told you the static head plus friction head, that is 58 plus 58, that is 116. So 160 will friction loss. Now you see, this is your static head, this is your friction head. So this is your pump performance curve. This is 500 gallon per minute. So your system resistance curve will be the static head plus friction, different flow, different friction losses will be there. For 300, friction loss will be this much. For 500, friction loss will be how much? This is 58. Static head is 58. So it will be around 100. How much meter? Now you see the discharge head will be in feet. They are giving in feet, that is in 373 something like that. 70 like that. You see, this is your flow, this is your head, this is your 381, and this is your flow like this. Then your best efficiency point. Now this is suppose you are providing a discharge valve. You see, providing a discharge valve here. So when you provide discharge valve, the friction loss is certainly going to increase. And so the going to increase. So upstream of the valve pressure will be high. Upstream of the pump pressure will be high. And if you draw the system resistance curve, initially it you see it is running earlier. If you see the earlier picture earlier, then it was running with this much 500, and your pressure was 381. But due to provision of this valve, there will be upstream pressure will increase. So pressure has increased to 381 to 430, and when it is 300 to 480, your flow will come down to 500 to 380. So if you provide the flow restriction in the discharge line, then pump will there will friction losses, and pump will the system resistance will cut here. And unless if there is no resistance, means no valve, nothing is provided, then it will, the operation point will be here, because it is the maximum rated flow. It is 500 rated flow. Here it is cut 500 rated flow. But once you provide the restriction, because this curve we are getting from the factory, they are using suction discharge line, and here also there is no, if there is no restriction in the pipe with suction discharge line, mostly it will operate at the system resistance curve will follow all operate at the rated flow. But once you provide the suction line, discharge line with isolation valve, elbows, etc., certainly upstream pressure will increase. When the upstream pressure will increase, flow will come down. So now you are going to provide to control valve. Control valve can be of two types: flow control valve, pressure control valve. Control valve CV value, every control valve having some CV value, and depending, and it has some set point. Once the demand increase or demand decrease, it will try to maintain the set point, and your CV value of this valve going to change, so that and so your friction loss, which happened earlier, that due to static installation of valve, elbows, etc. Here in this particular case, that it is continuously changing its CV value and position of the valve, so your pressure loss will be minimized. You see, this is the control valve. Now, how this it is for 0, CV value was 2, and when opening zero opening, CV value was 2. You see gradually the value is increasing. For 90% opening, CV value is also increasing. When the valve opening is increased, CV value is also increased. What is CV value? CV value means that suppose CV value, every valve, control valve having some CV value. Suppose the control valve having CV value 14. That what does it mean? And that it means the at 15.5 degrees centigrade, the valve from this valve, 14 gallon per minute flow will be there when upstream and downstream at differential pressure of upstream and downstream pressure drop will be 1. Upstream and downstream pressure will be 1. So you see upstream and downstream pressure will be 1. So depending upon the this is depending upon the opening the CV value is going to change and accordingly you are when providing a control valve, we are minimizing the pressure drop. You can see another one example is there. You see this is a 3-inch pipeline with times. This is the static pressure remains same. This is the differential pressure. Frictional losses you see it will go on decreasing. Differential pressure initially it was high, then it is going decreasing. You see initial flow was high due to restriction. The providing the isolation valve or whatever may be, control valve, it was too much, but if you provide a control valve, it will be slightly less. And it will go on changing the CV value also. You see the go on changing the CV value accordingly. So when you are changing the CV value, your flow will gradually minimize. The change of valve flow will minimize. Valve pressure differential is also minimize. Differential also initially it was high. Gradually when you are opening the control valve, CV value also opening and your pressure drop will also minimize. You see particularly for this particular case, you see this is the case where 3-inch valve, 0 case, its flow was 1007. You see flow was 1007. At that time, what was the performance curve pressure? The performance curve pressure was around 353.6. You see this is 353.6, and what is the system resistance curve here? Pressure, now it is how much? Now it is 334. So this is what is the differential? What is the differential pressure drop? Now this minus this is 19.4 feet. 19.4 feet means 8.593 PSI. 8.593 PSI differential. So like this, your pressure drop will also minimize, your flow difference will also minimize, because the control valve will try to maintain the set point by changing its CV value, changing its opening, and otherwise it go on your system. You cannot vary. It go on running with lower pressure, with higher pressure and lower capacity. I think I have discussed all the slides. If you go through each and every slides, your concept regarding the system resistance curve will clear. But if you still have some doubt, you can talk to me or you can write to me. I'll certainly reply you.